Okay, so number 5.
So like I know how to find the null of the space, but like I got confused.
Okay, so we want to find out whether W is in the column space,
Yeah.
whether W is in the null space, or neither.
Hmm?
Okay, so let's take a look at whether it's in the column space. So when we think about, how we're going to do this, what is the process? Do you know the process for doing this? Like, do you know what to do at all? Do you know what it means to ask if W is in the column space? Should we discuss what that even means?
Yeah.
Okay, so I'm going to write A down, and you, once you understand this, you'll find that it's really very uh, kind of natural because it's a natural extension of what we've been doing. So when we ask, is W in the column space of A? This means it's the same thing as saying, does AX equal W have a solution? Because for W to be in the column space means there are weights, i.e., the coordinates of X, that can weight the columns of A, because any weighted sum of the columns of A, it's also called a linear combination of the columns of A, is in the column space. In other words, are there weights x1, x2, x3, x4 that can weight the columns of A to build W? It's the same thing as saying, is W in the span of the set A1, A2, A3, A4, where the A1, the A2, the A3, and the A4 are the actual columns of A. I'm trying to make this in better focus. Does that make sense? That it's all the same question?
Yeah.
You know, this is what we need. We need W to be some weight, the first coordinate of X. See, X would be these weights times the first column of A plus the second weight, the second coordinate of X, X2, would be the weight on A2 plus X3 would be the weight on column A3 plus X4 to be the weight on column A4. That's what we need to find. So do you know how to find if AX equals W has a solution? Is that something you know how to do?
The one I did is like the null space one. Like I did it on the calculator, and after that I found out that.
Yeah, so let's go ahead and work on this solution. We're There are two ways to do this, but the easiest way to do it is just to go ahead and do a row reduction on the augmented matrix where we put A And then we put W because that's like our little B. That's our vector B that we're trying to hit with a weighted sum of the columns of A. So when you put this in the calculator, what do you get? I'm just looking to make sure I put that in right. Okay, it is. And it looks like there is going to be a solution, you see? So let's write that down. We get 1, 0, -1, 0, -2, 0, 1, -2, 0, -3, 0, 0, 0, 1, 1, and then a row of all zeros. Let's think about what that means, okay? This is the column that would be weighted, with x1, this is x2, this is x3, this is x4. So let's reconstitute. What does this first row mean?
So x1 minus x3 equal to -2.
Good.
X2 -2x3 equal to -3.
And x3 is free, right?
Yeah.
So x3 is it just itself, it's anything. And x4 is equal to 1. Do you see that?
Yeah.
So x, which is equal to x1, x2, x3, x4 is, all right, we solve for x1. So it's -2 plus x3. Just bring this negative x3 over to the other side, right?
So -3 plus x3, x2, -2. It's gonna be plus, right?
Yeah.
X.
X3 is just X3. And then what's X4 going to be?
X4 plus 1, -1.
No, it's the 1 is already over on the other side. We've already
Okay.
solved for X4. So, I mean, the point is we have a solution. In fact, we have infinitely many. We could split this up into a sum of two vectors. One of them is weighted with X3. So we have -2, -3, 0, 1, the constant term. So this is 0 plus X3. And then here we've got one copy of X3, so we put a 1 here. We have two X3s here, so we put a 2 here. We have one X3 here, we put a 1 here. We don't have any X3s in the fourth coordinate, so we put a 0 there. Does that make sense?
Yep.
And look. We have a solution. We have infinitely many ways to build this W, because we can use any value for X3 and it'll build this particular W. And in fact, this is a basis vector. But anyway, it's not quite a basis vector, sorry. But the answer is yes, W is in the column space of A because AX equal W is consistent. We have infinitely many ways to build W. Does that make sense?
Yeah.
All right. Now the next question is even easier because we're asking if W is in the null space of A, right?
Yep.
But that question is the same as asking, is AW equal to the 0 vector? It's the same question because that's what it means to be in the null space. Does that make sense?
Yeah.
So we just have to multiply A times W. We have to multiply this out and see. So again, using row vector multiplication, we can find those coordinates and see if they're all 0. So we're multiplying a 4 by 4 times a 4 by 1. The inside dimensions match. So this multiplication is defined. And the answer will be a 4 by 1. We're going to get a 4 by 1. So to get the first coordinate, this is the row 1, and there is only one column. Column 1 coordinate, we take row 1 of A, and we multiply it by this column, which is force W. So it's -8 times 1 plus 5 times 2 plus -2 times 1 plus 0, right?
Mm.
Now for the second coordinate, I mean, we can go ahead and check that and make sure it turns out to equal 0. Because if it's not, then we can stop, right?
Yeah.
But we've got -8 minus 2 more, which is -10 plus 10. So that is a 0. See? And now we check every single coordinate and make sure that they all turn out to be 0. All right, so how do we multiply it to get the second coordinate of AW?
Okay, -5 times 1 plus 2 times 2 plus 1 times 1. Mm, minus, no, plus -2 times 0.
Mhm. So we got -5 plus 4 plus 1.
0.
Mhm. So do we get 0 for the third coordinate?
You think? Yeah,
Okay,
think because yeah,
all right. So what do we get for the fourth coordinate?
0. Yeah, 3 times 1, 3, -4. 1 times 1 is 4. Yeah.
So the answer is yes. Since AW equals 0, W is an element of the null space of A.
Okay. Let me share my screen.
What?
I'm sharing my screen to for this question. Oh, you can see my screen, right?
Yeah, I can. So this is a question from
Yeah.
MyMathLab.
Yeah.
So given a set is a basis for the given set is a basis for a subspace. And we're going to use the Gram-Schmidt process to produce an orthogonal basis for W. So you can use the first, you can just take the first vector, right?
Yeah.
As your first basis vector. But now we need to build a vector that is in the same direction as 4, 7, -9, but that is orthogonal to 0, 8, 4. So this is what section, please?
6.4.
What?
6.4.
And this is the question number 2. So when it tells you to read, you know, in the book, like, do you ever use that option where it says, you know, help me, and then you read from the textbook? Do you know what I'm talking about? All right. At the bottom of the problem, there's either help me solve this, view an example, or get more help.
Okay.
So if you click get more help, it'll take you to the textbook because you can choose either textbook or ask my professor, right? And it'll take you right, you know, to the part of the book where it says how to do this. Okay. So we take the first vector, that's step 1. And that'll be our V1. That's our first one. Okay, so building an orthogonal basis. This is in the notes too. So I'm going to ask, yeah, good. You stop sharing the screen. Building an orthogonal basis. Now, if there's only 2 vectors, then we only have to do the Gram-Schmidt process 1. We're going to use the Gram-Schmidt process. We only have to do it once. So let's just it's a little more complicated if there's more than one vector, and we can do one of those too. All right. But here's an example. All right. So give me your vectors. What were they again?
0, 8, 4.
4.
Yeah.
And what was x2?
4, 7, -9.
So we're going to build an orthogonal basis for the span of x1 and x2. All right, so step 1. Take V1 equal to x1. So that's already done. You just take this one as your first one. But now step 2. Notice here that the span of V1 is the same as the span of x1 because they're the same vector. There's nothing deep going on with that. Step 2, we want to take, we'll call this space W1. We'll take the projection of X2 onto this space W1. Then V2 is going to be X2 minus the projection of X2 onto this subspace W1. Okay? Does that make sense?
Yeah.
Because this is the way that we do it, because we know that we can write X2 as the sum of two orthogonal parts. The projection of X2 onto any space W, in this case W1, plus a component Z. And this component Z is simply defined to be the difference between X2 and the projection onto W1 of X2. Just subtract, oops, sorry. Just subtract the projection from both sides. I meant to put the X2 first. Now the question is, wait a second, how do we even know that this lives in the right space? Well, X2 certainly lives in the span of X2. And the projection of X2 onto W1 lives in the span of X1, which is our W1, you see? So this does live in the span of X1 and X2 because it's built from X2 and a projection onto the line that X1 spans. That is span of X1. The W1 happens to be a line. It doesn't have to be, but here it is. It could be a plane or even a bigger space. But the point is, Z is orthogonal to X1 because Z is orthogonal to this, and this space is the space that X1 spans. In other words, Z is actually orthogonal to the space W1. Okay, that's the way that this construction works. We build X2 as the sum of two orthogonal vectors, one of which is the projection of X2 onto W1, and the other is going to be orthogonal to that. Well, we've learned that the projection of X2 onto W1, and in this case, the projection of X2 onto, X1 is the same line that is generated by X1. Any piece of that line spans the same line that X1 spans. And the projection of X2 onto the line that X1 spans is just a piece of that line. Okay, it's like the shadow of X2 onto that line that X1 spans. So how do we build the projection of X2 onto W1? Well, W1 is only spanned by X1, so we only have to do one of the dot products, right? So it's X2 dotted with the basis vectors of W1 because we're projecting onto W1, but there's only one basis vector. So it's just this one single weighted piece of X1. This is the shadow of X2 on the line that X1 spans, or on the vector X1. And this is how we get the actual length. This tells us how much of X1 x2 will fall down on when we shine a light on x2. So let me draw you a picture. If this is x2, we shine a light down onto x2, then what happens is that light is perpendicular to, say, x1. Then the piece of x1 that the shadow of x2 falls on, this piece right here, this is the projection of x2 on x1. But here it's actually all of w1 because all the w1 is the span of x1. So we'll say w1 because w1 is the span of x1. Does that make sense?
Yeah.
Okay. When we subtract this vector from x2, then what we're getting is this piece. This is the z. Just shift it over. If you draw it here from the origin, this is the origin. This is z. It's the same vector. It's just we just slid it over here so you can see that this vector that's x2 is the sum of its projection onto x1 plus this orthogonal piece. So this is the z. So now we just need to do the calculation. So you can see this, if you go to the book, you can see this in the book. All right, so how do we do this? So V2 is going to be x2 minus this projection of x1 onto, excuse me, of x2 onto W1. All right, so let's do it. X2 is 4, 7, negative 9, right? And we're going to subtract from that. Now we need x1 dot x2, so let's do that over here. And we need x1 dotted with x1. So whatever that fraction turns out to be, we're going to use that to weight x1. That's the piece. So this is the piece of x1 that x2's shadow falls on. So let's do the calculations over here. We need to find x2 dot x1. And then we'll need to find x1 dotted with x1. This is x2. This is x1. So when we dot x2 times x1, we just multiply the coordinates, right?
Yeah.
It's 4 times 0 plus 7 times 8 plus negative 9, what times what?
4.
Okay. So it's 56 minus 36. So what is that?
20.
Yeah. And now we're going to also find x1 dotted with x1 because we need that for the denominator here. So this is going to be a 20 here. Okay. So x1 dotted with itself means it's, the first coordinate squared plus the second coordinate squared, right? Because we're just multiplying x1 dotted with itself. We're dotting x1 with itself.
No.
Plus 4 times 4. So what is that? 64 plus 16. So this turns out to be a really nice fraction. This is 1/4. So it's 4, 7, negative 9 minus, Well, 1/4 of 0 is 0. What's 1/4 of 8?
Mhm.
Just divide 8 by 4.
2,
Yep. And what's 1/4 of 4?
1.
Good. And now we just do the subtraction. And this is going to be our second basis vector, v2. So our final answer is this, orthogonal basis. It's going to be the set v1, v2, but v1 was x1, and v2 we just built. And it's orthogonal because it's the z. Does that make sense?
Yeah.
So this is actually problem number 2 from MyMathLab 6.4, you said?
Yeah.
Because that's the Gram-Schmidt process. Now, it's more involved if there are more vectors. This is pretty easy because we only had 2 vectors in our basis. Do you want to look at the problem where there's more vectors?
Yeah.
All right, I think that's going to be like problem 3. No, problem 3 is also let's see. Question 3. No, it's still just 2. It's the same, but you can work on problem 3 now the same way. Question
Yeah.
3, right?
Yes.
All right, but is there one where it's 3?
I think it's
Yes.
problem 5.
Yeah, number 5. Let's
Yeah.
do number 5. So we want to find an orthogonal basis for the column space of this particular matrix. And yeah, I mean, I needed to give you a chance to practice with more, you know. And we did one like this in class, but we can go through this. Now, I don't know what your numbers are, but I'm going to use these and then you can practice, okay?
Okay. Yeah.
Because it generates different problems. But let's just work through an example. And also, let me share my screen with you because I want to show you what you can do. Okay, so let me move this out of the way. All right, so what you can do is you can click Get More Help, okay, and Textbook. And it'll take you right to the examples in the textbook. See, this is the Gram-Schmidt process. And here is a situation where it's 3 vectors, okay? So it's going to, we have 3 vectors in this matrix A. So we want to go through the process, but it gets a little more involved after we have gotten V2, because once we've gotten V2, because it's got to be orthogonal to V1, and that just takes us one little step, okay? When we get to trying to find V3, it is more involved, because now to build V3, we have to build the projection of X3 onto the space, not W1, but the space W2. But what is the space W2? It's the space that's spanned by the V1 and the V2 that we built. You see? So we'll find that projection. And so the Gram-Schmidt process says we're going to have to do this dot product thing, both with V1 and with V2. And then we subtract that projection from X3 to build V3. Okay, so we'll go through that. All right. But I'm just saying it can be really helpful.
Yeah.
All right, so here we go. We're going to let V1 equal X1, okay? This is vector X1, not a coefficient, okay? It's the vector. And this is the vector X2. And this is the vector X3. These are the basis for the column space of A. Now, one of the things that we might want to do is just double check that these are actually linearly independent from one another and make sure that the dimension of column A is really 3. So let's check that these are linearly independent, okay? Now, a quick way to check would be if their dot products were all 0, because if they're all orthogonal, they're all linearly independent, right? But their dot product isn't 0. I can see that right away because, you know, these two cancel out, but then we'd have 8, which isn't 0. So we can't use that. So what we can do, though, is we can put this matrix in, right, and see that when we row reduce it, that we don't get something that's not solvable for every single B. In other words, what we're checking for is we're checking for a pivot in every single column. It's not, we're not going to get a pivot in every single row, but linear independence means we'll get a pivot in every column. So we can check that. And I think that it turns out that it is. Okay. All right. Now, step 2. We're going to let W1 be the span of X1, or that's the same as the span of V1. All right, step 2, we're going to find V2, which is going to be X2 minus the projection of X2 on the line that's spanned by X1 or V1, which we're calling W1. All right, so this is good practice. Shall we do that?
Yeah.
And then once we do that, then for step 3, we're gonna let W2 be the span of the W1 and the W2, whatever W2 turns out to be. We're gonna let W2 be the span of V1 and the V2, whatever that V2 turns out to be. And then finally, here we're gonna let V3 be X3 minus the projection onto W2 of X3, because this is orthogonal to W2, okay? But check it out. This projection now is onto a space that's got 2 vectors in its span. So this is going to be, right, the projection of X3 onto V1 plus the projection of X3 onto V2. In other words, it's going to be X1 dot X3. Well, I'll put the X3 first, but even though it doesn't matter. X3 dot X1 divided by X1 dot X1. That's going to weight x1, that's the piece of x1 that x3 projects on, okay? This is the projection of x3 onto the span of v1. Oh, I should put v1 here. I should put hang on. This is yeah, I better put v1 here because it's v1 now. Well, v1 is x1, okay, but I'll just write v1 because when I get ready to do x2, this other piece, I've got to use v2. So I'll go ahead and use v1 here, even though it is x1. I mean, you know, you could leave it as x1, but it's really the projection of x3 onto the span of v1. And then we want the projection of x3 onto the span of v2. And v2 is not x2, right? That's why I'm saying I just want to be consistent here. So this is going to be x3 dotted with v2, whatever we find for v2, over v2 dotted with v2, and that's going to be the piece of v2. See, we weight v2 with that to find the shadow of x3 onto v2. So the sum of these is the projection of x3 onto the whole space that's built with v1 and v2. Does that make sense?
Yep.
Great. All right, let's do it. And of course, you know, if we had another, you know, if we had a fourth vector here, then we would need to do this, but we would be having three pieces, right? We would have the shadow of x4 onto v1 plus the shadow of x4 onto v2 plus the shadow of x4 onto v3 if we had like a fourth vector. Okay, so let's do our solution. This is the general process that you can follow for three vectors. All right. So you're going to help me here? V1 is going to be x1, so it's just going to be this. 1, -1, 0, 1, 1. Okay. This is going to take a lot of paper. That's okay. Now, V2 is x2 minus the projection onto V1, which is x1 of x2. So V2 is x2 minus the projection, right, of x2 onto W1. So we're going to let W1 equal the span of V1. All right, so what is that going to be? Let's see. Well, x2 is the vector 2, -2, 2, 4, 4. Okay, and now we're going to subtract this projection. And so we have a coefficient times V1. What this is going to be, right? It's going to be x2 dotted with v1 over v1 dotted with v1, and that's going to weight v1, which is x1. All right, so we need to calculate x2 dotted with v1. This is x2 minus this dot product times v1. Okay?
Okay.
All right, let's do it. What's x2 dotted with v1? Well, that's the same thing as x2 dotted with x1, right? So what is that? Well, here we go. Here's x2, here's x1. We can see them.
2 times 1.
What? 2 times 1? Okay.
Oh, we're
Yeah,
going
yeah.
that way.
Yeah, no, that's right. It's 2 times 1 because it's x2 dotted with x1 because
Yeah.
x1 is v1. So it's 2 times 1,
Plus -2 times -1.
-2 times -1.
Plus 2 times 0.
Good.
Plus 4 times 1. 4 times 1. So 4 plus
These
4.
go away. No, no, no. This is a -1 times a -2. So this is actually 4 plus 4
Yeah.
plus, right? It's 12, right? What about v1 dot v1?
So
You can just square these, right? It's 1 squared plus -1 squared plus 0 squared plus 1 squared plus 1 squared. You can just square the
it's
coordinates.
4.
Yeah,
So 12 is 3. It's
yeah,
gonna be 3 or
yeah. It's going to be 3. So we're going to multiply this vector times 3.
okay.
I'm going to run out of room. So minus, we're subtracting. So it's 2, -2, 2, 4, 4, minus 3, -3,
-3
0, 3, 3.
plus -1 minus -3.
What's -2 minus a -3?
-5 or
Are you guessing? -2 minus a -3. This is a real problem.
oh, so
No, I mean, it's a problem. If you can't do it in your head, you should write it down
okay.
because this is 8th grade math. I'm not even kidding. I'm getting that. Are you getting the same thing?
Yep.
All right, so now we have V2. And V2 is pretty enough that we'll just keep it the way it is. It's not like we need a V2 prime or anything the way that we did in class. No, seriously, if these kinds of calculations, if you have a problem with doing them in your head, just write it down. It doesn't take long. All right, and that way you can see it and carefully distribute, negative signs and all that good stuff. So this is V2. Now we're going to find V3. V3 is going to be X3 minus the projection onto W2 of X3, where W2 is going to be the span of V1 and V2. So now we're going to find this. Okay, great. So let's work on the projection first. The projection onto W2 of X3. It's the sum of the projections of X3 onto V1 plus the projection of X3 onto V2. So it's X3 dot V1 over V1 dot V1. That's the shadow. That's a piece, and multiply that by V1. That's a piece of V1 that X3's shadow falls on, plus x3 dot v2 over v2 dot v2 times v2. Okay. So we need to find x3 dot v1, and we need to find x3 dot v2, and we need to find v1 dot v1 and v2 dot v2. So we need to see x3. Let's write x3 down where we can see it. It's 5, 1, 3, 3, 7. That's that third column of A, right? So we can see x1, we can see x2, and we can see x3. So we can do these calculations. This v1 is x1. Oh, and it's not actually x2 we want to see. We want to see v2. This is v2.
Oh,
Right? Because we're using the v's, you know? Okay.
okay.
So x3 dot v1.
V1 is
Here's x3. Here's
so 5.
v1.
Yeah. 5 times 1
Uh-huh.
plus 1 times -1
Good.
plus 3 times 0
Good.
plus 3 times 1
Good.
plus 7 times 1.
Great. Let's figure out what this is. 5 minus 1 is 4 plus 10. Now, we already figured out what v1 dot v1 is because we already did that up here. So 14 over 4 is 7/2. So that's going to be our coefficient that's going to weight v1. Okay. Now, what is x3 dotted with v2? Here's our v2. Here's our x3.
So, okay. 5 times -1 plus 1 times 1
Good.
plus 0. What was it? 3 times 0. Oh, times 2.
Yeah, we've changed vectors.
Yeah. And 3 times 1
Good.
and 7 times 1.
Excellent. We can also just look here and see the,
Oh, yeah.
did we do this right?
5 times 1. V1, right?
Oh, no, this is v2. We can't just look here. Okay, fine.
Mm.
We can look for the x3 coordinates, but
Yeah.
we can't look for the, all right, so what does this turn out to be? -5 plus 1 is -4, right?
Yes.
Plus 6 is 2. Plus 10 is 12. You just put it in the calculator if you need to.
So V1 times.
So it's -1 times -1 or -1 squared, right?
Yeah. 1 square plus 2 square plus 1 square plus 1 square.
Great.
That's gonna be 4.
4, 5, 6, 7, 8.
Yep.
So 12 over 8.
It's gonna be 3 over 2.
You got it. So now we're ready to use these numbers to find the projection of x3 onto w2, but then we have to make that last step where we subtract that from x3, okay? So it's 7/2 times v1 plus 3/2 times v2, right? Because we use these to weight v1 and v2, right? And v3 will be, you know, this is the projection of x3 onto w2, this whole thing, right? All right, so let's do this. We've got x3.
5.
Okay, V1 was X1.
Oh, one, 0, 1,
Okay, right? And V2 was -1, 1.
1, 2, 1, 1.
Oh, great. We're getting there. All right, keep going.
Um, 5. Okay.
All right, what do we got? Oh, this is going to be gross. Now, there are ways to make it easier. For one thing, the span of these vectors is the same as the span of any of their multiples, right? So, I mean, we don't really have to multiply by 7/2. Okay, we could just, but we're gonna do this. Okay, we're just gonna go ahead and do this. We would have had to make adjustments before we calculated the dot products. And honestly, we never would have seen that these were what they were. So we really actually couldn't make this much easier, to be honest. We
Okay.
would have to be able to see into the future to have been able to do that. So, all right. You don't have to do all, you don't have to do all these steps, but I'm just being super careful. All right. So we're going to add these. What's 7/2 minus 3/2?
So 4.
Uh, 4/2,
4. Yeah.
which is 2. Right? 4/2 is 2. So it gets prettier. What's minus 7/2 plus 3/2,
So -4 halves.
which is
-2.
excellent. See it?
Yep.
And now we're ready to find V3. Finally. 5 minus 2,
3.
1 minus a -2.
-1. Oh, plus 3.
I suggest that you always do that, okay?
Okay.
3 minus 3,
0.
3 minus 5.
-2.
Good. 7 minus 5.
2.
So finally we have our basis for the span of the original. Actually, it's a basis for column A. We can just say that. It is going to be the span of V1. Oh, the basis is just the set. Sorry, the whole column A is the span of that. We just want the basis set. We don't need to say span here. So it's V1, V2, V3, and we found them. V1 was X1, right?
Yeah. Mhm.
this x1.
Yeah,
So, this is V1. V2 was negative
negative
1.
1, 2, 1, 1.
Yeah, luckily we can just look right back here and see.
Yeah,
And then V3.
3, 0.
All right. Good. I'm glad that we went over that because you definitely need to understand how to do this.
Yeah,
Do you have any other exams today?
yeah, at 5.
You have an exam at 5.
Yeah.
So, what would you like to do next? You want to go over something else from test 2?
The test 3.
Test 3. Okay.
It's almost like,
And, we can still meet in the morning.
hmm?
We will still be able to meet in the morning.
Tomorrow, right?
Yeah, in the morning. Let's meet a little earlier, shall we?
Yeah.
So, which problem are you looking at in test 3?
The question 8.
Okay, let's look at question 8. All right, so this was a specialty kind of problem where you need to understand that there's something very special that happens if a matrix A has a certain form. And notice A is not quite symmetric. Now we learned about symmetric matrices. Did you do okay with the stuff with symmetric? Oh, you haven't gotten to section 7.1 yet.
No.
Oh, okay. Well, there's definitely going to be a question about symmetric matrices because they're really special too. But when a matrix A is a 2 by 2 matrix that has exactly this form, we learned that this means something special. It means that this is really some kind of a rotation matrix. And in fact, there's a whole bunch of stuff. Now, A and B are real. And this is what's so fascinating, is that when A and B are real values and A looks like this, then the eigenvalues are actually a complex pair where lambda equals A plus or minus BI. And R is the norm of the excuse me, did I say eigenvalues? Yes. It's the norm of the eigenvalues, and it's the square root of A squared plus B squared. And further, A can be written as R times, well, obviously, you can pull out a factor of R with any matrix, but what makes this so special is that this part is actually a rotation. This is the same thing as a scaled rotation through theta degrees counterclockwise, because this can be interpreted to be this. It only works for a matrix that looks just like this, but it always works out. Because you can this can be a cosine value, this can be a sine value. The reason we pull out the R is to make these values scale between -1 and 1. I mean, that's the whole point of pulling out the R, is because for these to be cosine and sine values, they have to be between -1 and 1. Okay. But anyway, I gave you all of this. Okay. And the other thing is that negative pi is less than or equal to theta is less than or equal to pi. So we're going to, pick a theta, but not between 0 and 2 pi. We're going to pick it by convention between negative pi and pi. But the point is, we just need to understand, what's given here. And I forgot to give you the matrix A. So I gave you the matrix A on the board. I was so busy writing all that other stuff. And the matrix A that I gave you is a matrix that you need to understand the cosine and sine values for a particular theta. There's only two reference triangles you need to understand from trig. But the first thing we want to do is figure out what R is, because if we need to, we're supposed to pull out an R. But R is the square root of a squared plus b squared. Well, what's A? A is negative square root of 3 over 2. B is negative 1/2. So R is the square root of negative 3, a square root of 3 over 2 squared plus negative 1/2 squared. Of course, these are going to become positive, once we square them. So R turns out to be the square root of, well, 3/4 plus 1/4, because when you square root of 3, it becomes 3. When you square 2, it becomes 4, right? So when we square a fraction, it's the numerator squared divided by the denominator squared, right?
Yep.
And same here. Oh, but what's 3/4 plus 1/4? 1. So R is actually 1. So I made this super easy where you don't even really have to pull out the R because it's just a 1. So all we had to realize is that cosine theta has to be negative square root of 3 over 2. And sine theta has to be this value, negative 1/2, because B over R and A over R are just the A and the B that are given because R was 1. So this is a particular theta that has these values. So you just need to know this triangle. I'm going to try to draw it a little bit better. There's two reference triangles that you should know. All right. And one of them, I think I drew it the other way in the solutions, but we can draw it this way. This is the 60-degree angle, right? Pi over 3. This is the right angle. And this is the 30-degree angle, pi over 6. Now, the sine of pi over 6 is 1/2. The sine of 30, if you just remember a couple of things, you need to remember that the sine of 30 degrees is 1/2. And you also need to remember that the sine of 45 is square root of 2 over 2. Okay. I mean, you really don't have to know much more than that because you can figure out all the other ones by knowing that. But this is side length 1 because sine is opposite over hypotenuse. This is 2. And this is square root of 3. Cosine is adjacent over hypotenuse. Okay. So this reference angle is theta. But now, once we figure reference angle theta is pi over 6. It's 30 degrees. Now we just need to figure out what quadrant it is in order to pick the actual correct theta. This is trig. Did you take trig in high school?
Hmm?
Did you take trigonometry?
No.
Oh my gosh, you
I
didn't
took
take
like algebra, I think algebra 1 to 2.
what?
I took algebra like algebra 2.
But you never took trig?
No.
So you're not going to ever take calculus?
Oh, I took calculus in
How did you
college.
pass calculus without knowing trig?
Oh, well, yeah, I did. I really forgot maybe.
It's amazing. Well, anyway, listen, in the first quadrant, both sine and cosine are positive. All of the trig functions are positive in the first quadrant. In the second quadrant, sine is positive, okay? In the third quadrant, tangent is positive. And in the fourth quadrant, cosine is positive. all students take calculus. That's how we remember. They're all, sine, cosine, and tan are all positive in the first quadrant. Sine is positive, cosine and tan are negative in the second quadrant. Tan is positive, but sine and cosine are both negative. But that's okay, because tan is sine over cosine. So negative over negative, it turns out to be a positive. And in this fourth quadrant, cosine is positive, but sine and tangent are negative. So anyway, the point is here is the quadrant where cosine theta is negative and sine theta is negative. So we need a reference angle of 30 degrees that's here in this third quadrant. And that's going to be, well, let's just figure it out. 3/6 gets us halfway to pi, right? 3/6 pi gets us halfway to, well, a negative pi. And then we add two more because we want it to be a reference triangle that's pi over 6 here, but we count it this way as negative 5 pi over 6. So theta is negative 5 pi over 6 to get to a reference angle of pi over 6 in the third quadrant, if we want it to be between negative pi and pi. I don't think I'm going to give you this on the final exam. We've got way more stuff to cover on the final, okay? We got, this was a very special case of a very special kind of matrix that turns out to be a rotation. So I'm not planning to put this on the final exam. All right, just FYI. Also, it relies so heavily on trig. You aren't the only student in the class that has some issues with trig. Just FYI. Okay. Other questions?
Mm.
I'm just
What
going
about,
to. All right, what we got?
oh, number three, like I kind of start, no, number four.
On
I
the
get it
test?
at I did it like at the first way. I get it. Some of them are like, I couldn't finish it.
The characteristic polynomial and the
Yeah.
eigenvalues?
Yes.
So the characteristic polynomial is the determinant of A minus lambda I, right? That's true, for any matrix, right? So you were able to get the characteristic polynomial? Here we go. A minus lambda I. So A is a 2 by 2. So the lambda gets multiplied by the 2 by 2 identity matrix. Because we can only subtract a 2 by 2 from a 2 by 2, right?
Yep.
So it's 9 minus lambda minus 4, 4, and 7 minus lambda. Do you understand how that just happened?
Yeah.
So now we're going to find the determinant of A minus lambda I, right? It's this times this. So it's 9 minus lambda times 7 minus lambda minus, right?
Yeah, I get it.
4 times negative 4, right? So we have to be careful with these signs. That's why I made this minus really big, right?
Okay.
So when we distribute 9 minus lambda across 7 minus lambda, we get 9 times 7 is 63, right?
Yeah.
9 times negative lambda is negative 9 lambda. Negative lambda times 7 is
So 9 that. Oh. So
what's negative lambda times 7?
negative lambda. Negative 7 lambda.
Good, good. I know, I'm putting you on the spot. And then what's a negative lambda times negative lambda?
Lambda square plus.
And then what's this going to be? The negative times the negative.
It's positive 16.
Nice. So what is this?
So lambda
Lambda.
square.
Mm-hmm.
Okay. So
73, 79,
you,
right? Because 63 plus 10 is 73. And then plus 6 more is 79.
okay.
So we got to use the quadratic formula. A is 1. B is negative 16. And C is 79. So quadratic formula is that lambda is going to be negative b plus or minus the square root of b squared minus 4 times a times c, whole thing over 2a, right?
Okay.
So it's negative 16 plus or minus the square root of negative 16 squared minus 4 times a, which is 1, times 79, which is c, over 2 times a, which is 2. It's negative 16 halves plus or minus the square root of, so we just use a calculator, right? 256 minus 4 times 79. What's 79 times 4, right? 36, remember the 3. What is it, 316? So this is 50,
50.
negative 50,
Oh, yeah.
isn't it? Did I do that right?
3.
Did I do that right? Or is it negative 56, 60, negative 60?
Yeah. 0 over 2.
But the thing about negative 60 is negative 60 is 4 times negative 15, right?
Yeah.
So we can pull out a 2. And those 2's cancel. So it's 8 plus or minus square root of 15 times I. You can pull out the negative 1 as I. So those are our lambda values. 8 plus square root of 15i and 8 minus square root of 15i. You can call them lambda 1 and lambda 2 if you want. That's all. This was the characteristic polynomial. And these were the lambda values. You just had to use the quadratic formula. I didn't ask you to find the eigen spaces or anything, the basis for the eigenspaces, even though I did that on the solutions. You didn't have to do that. Did that answer your questions, or did you want to understand about the eigenspaces basis?
Can you explain more about it?
The eigenbasis spaces? Sure.
Okay.
So in order to understand the eigenspace basis vectors, we have to use these different eigenvalues as the actual lambda in this equation, in this matrix, because this will be A minus So let's do it for, lambda 1. So A minus lambda I is going to be A, which is minus now our lambda, which is 8 plus square root of 15i. And then we have a minus 4 here. And here we have a 4, because we're not subtracting lambda. And here we have 7 minus 8 plus square root of 15i. All right, so when we reduce that to look at what that really turns out to equal, this is lambda 1. 9 minus 8 is 1, so this first coordinate is 1 plus square root of 15i. Second, this coordinate's of course negative 4. This is 4. And 7 minus 8 is negative 1 minus square root of 15i. Now it turns out that because we have eigenvalues, we know the null space is not the trivial null space. Okay, because we can't use an eigenvector that's 0. We know we have non-trivial eigenvectors because we have eigenvalues. So we know that these two columns are linearly dependent, but that means their rows are as well. So we can just pick one of these rows and figure out, what that means. And we're talking about the null space, so we put zeros here. So if we use row 1, and I don't know what I used, in the solutions, but if we use row 1, it says 1 plus square root of 15i times x1 minus 4 x2 is 0. Okay. Well, I'm going to solve for x2. All right. So 1 plus square root of 15i times x1 is 4x2. I don't want to divide through by a complex number, but I don't mind dividing through by 4. That's why I'm solving for x2. So x2 is this times x1. What is this? It's 1 plus square root of 15i on the top divided by 4. So that tells me that x, which is x1, x2, is, well, I'm just going to use x1 for x1, and x2 is going to be 1 plus square root of 15i over 4 times x1. So we can pull out the x1 as our parametric variable, and we have 1 for the first coordinate, and we have 1 plus square root of 15i over 4 for the second coordinate. So this is the basis for the eigenspace. It's the basis vector for the eigenspace associated with lambda 1, which was 8 plus square root of 15i. Right, so the eigenspace basis would just be this single vector. The basis vector for the eigenspace for lambda 1. Now we don't even need to do the work for the basis vector for eigenspace for lambda 2 because we know that the eigenvectors are also going to be complex conjugates of one another. So you can just take this and put a minus here instead of a plus. And that will give you the basis for the eigenspace associated with lambda 2. You just change the plus to a minus. So if you find one of them, then you found the other one. It's a complex conjugate. Well, 1's not a complex number, so it is its own complex conjugate. But the complex conjugate of this number, you just put a negative instead of a positive in front of the component that has the I in it. So you don't have to, go through all this again. You just take this and make it negative where the component involving the I sits.
Okay.
And there was, a homework on this. That was homework 5.
Yeah.
Other questions? Okay, so again, about 25% of the test is going to be from each test that we had, and then 25% is going to be on the new material, and 7.1 is more important than 6.5. Okay, so we're looking at test 2. Number 7. So cofactor expansion. Okay, so here we go. We want to find the determinant using cofactor expansion. So, it's a 5 by. 6, 9, 2, 8, 4, 0, 0, 0, -5, 2, 2, -4, 0, 6, 3, 4, 1, 0, 7, 2, and a bunch of zeros. So there are kind of 2 obvious ways to solve this problem. One obvious way to do it is to, look at cofactor expansion along row 3. Okay, that would be one way to do it.
Yeah.
Or we could expand along column 5. Either way, we're dealing with lots of zeros, right? So you pick the row or the column that has the most zeros. So how about I solve it in a different way
Yeah.
than it's solved in the solutions? So how about we expand along column 5? Just so I can show you 2 different ways to do it. So we're going to expand along that column. First thing that we do is we look at the location of any non-zero entries there, because we have to weight those with plus or minus 1 depending upon their location. So plus, minus, plus, minus, plus, minus, plus, it's minus. This is going to be a -1, right? So we go plus, minus, plus, minus, plus, minus, plus, minus. Another way to think about it is 1 is in the position row 4, column 5, right?
Yep.
So you take -1 and you raise it to the 4 plus 5. And then you just multiply 1 times that. If this had been the 2, then you plus, minus, plus. This one was positive. It was actually a little easier, but that's okay. There's a negative that's going to pop up one way or the other. But the point is, this turns out to be -1. So it's -1 now times the determinant of the matrix that we get when we delete this row 4 and this column 5 from the original matrix, okay? So when we delete that, then we're left with a 4 by 4 that's 6, 0, 2, 4, 9, 0, -4, 1, 2, 0, 0, 0. And then what would be the last row? We're taking out that row and that column. What would be the last row?
4, 2, 3, 2.
Great. So now what we need to do is find this determinant. Again, we pick a row or a column where it's, easy with lots of zeros. So how about we pick column 2?
Oh, okay.
Okay, because it's different than the way I did it. So plus, minus, plus, minus, plus. So it's going to be plus 2 times the determinant of the 3 by 3 that we get when we delete row 4, column 2, because that's the only non-zero entry. So it's 6, 2, 4, 9, -4, 1, 2, 0, 0. So we can just keep going. -1 times +2 is -2. And now we pick a row or a column that's easy. Obviously, it's going to be row 3 because there's only one non-zero entry, namely the 2, right? Plus, minus, plus, so it's +2. Now times the determinant of this 2 by 2 matrix once we get down to a 2 by 2 matrix. Then we can use our formula. So it's -4 because -2 times 2 is -4 times what? 2 times 1 minus
It's
-4 times 4. What does this become?
Okay. Positive. So -4 times 18. It's gonna be 37.
Yep. So we've been at it almost 2 hours, not quite. I think that that is about all the time I can spend on this today. So why don't we meet in the morning at like 9:45?
Tomorrow?
Mm-hmm.
Okay.
Is that okay? 9:45 or 10?
Yeah, it's fine.
All right. That'll give us, an hour and a half before we both have to leave.
Okay.
All right, I'll see you at 9:45 in the morning.
Okay, thank you so much.
You're very welcome.